Okay, we have just one task to complete still before we are ready to do our vertical jumping simulations. We need to modify how we're specifying the initial state of the model so that it's starting in an initial static squatted pose that's conducive to simulating a squat jump. To remind you of where we're at, we are already specifying an initial state, kind of obviously. We wouldn't be able to do a simulation without an initial state, but it's not the initial state that we need. So right now, our simulations look like this. And we need to specify the initial state now so that the model is not starting in mid-air and falling to the ground, but that it's starting on the ground, supporting its weight with its contact force and holding that static squatted posture ready to do a vertical jump. I'm going to make one change here to the model function before we go. You can see here on the left, it's giving me, when I run the simulation, it's giving me not some errors, but some numerical warnings. I'm saying the matrix is singular. That's related to inverting that mass matrix that we talked about a couple lectures ago. Those warnings are resulting from the formulation of the contact model. So if I go here into my model function and go down to where I'm specifying the vertical contact force, those warnings are coming from this exponential damping term here. And I'm going to replace that with a linear approximation here. I'm going to replace the exponent with 1 minus the damping coefficient times the velocity of the contact point. This is a decent approximation of that exponential function for the range of velocities that we typically encounter in these types of simulations. Exponents is something that a colleague who does a lot of modeling like this once advised me to avoid in forward dynamics simulations like this. You should really only use exponential functions when you really need an exponential function, because they can sometimes give you some numerical headaches that lead to warnings and issues with your model behaving nicely from a numerical perspective. Okay, so make sure you make that change there in your contact force. If you don't, it'll probably still work. It might still give you some warnings here and there. They're nothing to worry about, but when you get into doing actual jumping simulations, it might cause you some problems. Okay, let's revisit our initial state here. And if you looked at the document that I posted earlier this week, it gives you some guidelines there for specifying the initial state. Some of you noticed that those aren't really like verbatim chunks of code that you can copy paste in here. There's a little bit of footwork you still need to do. And I actually just noticed this morning that there was one pretty important error in there that's going to cause that code to not work very well, even if you were to run it verbatim. So let's kind of start from scratch here and see how we would specify an initial static squatted pose of our model. We'll start here with the kinematics, and let's just remind ourselves here what these kinematic variables are here, these generalized coordinates. Q1 is the initial horizontal position of the hip. Call that hip position, and we specify that in meters. And Q2 is the initial vertical position or initial height of the hip, and we also specify that in meters. Q3 is the initial trunk angle relative to the global coordinate system, and Q4 and Q5 are the initial joint angles, the initial angle of the hip, and the initial angle, or the initial angle of the knee. Now on the units here for the angles, I have degrees specified there. I do that just because we are mostly familiar with thinking of angles in terms of degrees rather than in radians. So the number that you will actually specify here will be these numbers in degrees over here. It then converts those numbers to radians, because radians is what the function needs and what the integrator needs. So it's actually passing a value here that's in radians, but you'll be specifying it here in degrees. If that's confusing to you to have degrees over here, you can go ahead and change that to radians if you want, because the actual value that it will store in the variable here is going to be in radians, not in degrees. But you'll specify it here in degrees if you're changing these numbers on the left there. Okay, a few of these values we can specify completely arbitrarily. Only one of them really has no effect on the simulation at all, and that's this Q1 variable here, the initial horizontal hip position. That just kind of defines where along the ground the model starts its jump, and it really doesn't affect the muscle forces or contact or anything like that. So we can just give that an arbitrary value. We'll just start it at 0. Q3 here, the angle of the trunk, we can specify that arbitrarily. And I'm going to leave that at 80 degrees here from the right horizontal. This value will have an influence on the results. The initial squatted posture will affect what the maximum possible jump height is. But it's one that we can freely specify here and don't have to worry about what the other values of the initial states are. So we can pick this one, Q3. Likewise here, Q4 we can also pick, and that's the initial angle of the hip. And again, the value here will have an effect on the results. It'll affect what's the maximum jump height we can get, but it's one that we can freely specify and still be able to do simulations if we define our other states here correctly. Now, in terms of defining those states correctly, these other two initial states that I haven't yet set, Q2, the initial vertical hip position, and Q5, the initial knee angle, those are ones that we cannot freely specify. These are ones that we have to compute from the other values of these states and from the mechanics of the model in order to get it to be in a static squatted posture. So let's work out how we specify those initial states here, Q2 and Q5, the initial vertical hip position and the initial knee angle, respectively, to get the model in an initial static squatted posture. Okay. I'm going to do Q5 first. So we're going to specify initial knee angle. And the way that we're going to do this is, let me set my simulation time here to a real short time and run it, and so hopefully we'll get a picture here. Okay, the way that we want to do this is this model here has a center of mass that's going to be roughly located where my cursor is here, slightly above the hip and slightly in front of the hip. And it also has a contact point here down on the bottom of the foot that generates a ground reaction force. For the model to stand still, the ground reaction force here needs to run directly through the center of mass. Okay? When it does that, the ground reaction force will be aligned with the other external force acting on the body here, the gravitational vector, the weight of the model. And this will cause it to stand still in a squattic pose. Okay? So we need to specify an initial state here where the foot is directly underneath the center of mass and where the initial vertical ground reaction force is exactly equal to the model's body weight so that those balance to 0, and where the initial horizontal ground reaction force is 0. So there's no net force in the horizontal direction moving the model in the anterior-posterior direction. That horizontal ground reaction force, remember that force, Fx1 here, is a function of the horizontal velocity of the contact point, which is a function of just generally a function of the horizontal speed, or the generalized speeds of the model. So we take care of that one here by setting all of these initial generalized speeds to 0, which also makes sense for our initial static squatted posture. It's a static squat. The model is not moving, it's static, so all of its initial speeds here should be 0. Okay, so we don't really have to worry about that initial horizontal force. The initial vertical force, we're going to take care of that by specifying the value of Q2 here so that our contact point is pressed just exactly deep enough into the ground so that the initial vertical force is exactly equal to body weight. And we're going to specify Q5 here such that the location of this contact point, which we can manipulate by changing the knee flexion angle there, is aligned horizontally with the horizontal position of the center of mass. Okay, that'll place my foot here directly underneath the center of mass. It'll cause my vertical ground reaction force to run straight up through my center of mass. This will result in my ground reaction force not producing any moments about the center of mass, which will allow my model to stand still if I specify the right initial joint moments here at my joints, which we'll deal with after this. But for now, we're just going to get it with the right initial kinematic states here. Okay, so to specify my initial knee angle, I need to get the horizontal position of that contact point, P4, equal to the horizontal position of the center of mass. Both of these expressions here are functions of Q5. And so if I have this expression here, I can solve it for an initial value for Q5. There's a number of ways you can do that. Some of you have contacted me with your particular approach that you're using. Some of them worked well, some of them didn't work so well. What I'm going to show here is my particular approach to getting this initial value for Q5. This is what I do. It's what seems to work well for my simulations. There might be other ways of doing it that you'll do that will differ from this in subtle ways or dramatic ways, but might still get you a good initial value for Q5 or the quote-unquote correct initial value for Q5. So don't worry if you end up doing this a slightly different way than what I show here. This is a way that I use that I think works pretty well, but there's lots of ways of solving this equation and getting an initial value for Q5 that'll work, and that will probably get the same value that I'll get here. So don't worry too much if you're doing it a different way. This is just the way that I like to do this. So I'm going to start a new script here, and we're just going to clear it out. And I'm going to derive an expression for Q5 from this equation here, from the initial horizontal position of the foot equaling the initial horizontal position of the center of mass. Okay. Now, we already have here an expression for the horizontal position of the foot. If I go to my model function, or sorry, if I go to my model go function, down here when I do my plotting, I've already got an expression for P4x. Okay? That's my horizontal position of my foot, so let's copy that over here. I need to form an expression for the horizontal position of the center of mass. Okay? There's no way that I know of in PyDie to get it to spit out an expression like this that gives you the position vector of the entire center of mass of a multi-body system like we had here. I thought there might be. It seems like something that might naturally be in there. I wasn't able to find it. I actually contacted the PyDie creator who I know, and he said, well, it looks like we don't actually have that in here. So a way around that is to derive an expression for the center of mass of each body here in the model, and then the center of mass of the entire system of all of those bodies linked together is just the average of the center of masses of the individual body segments weighted by their masses relative to the whole body mass. Okay? That's not as complicated as it sounds. If I go back to my PyDie code here, which I think I have open, yeah, right here. Down here at the bottom, I've asked PyDie, where I'm having it export my kinematics of points of interest. I've added here to the bottom, it's exporting 3 additional kinematic points of interest. It's giving me the horizontal positions of all 3 of my centers of mass. For body A, which is the trunk, for body B, which is the thigh, and for body C, which is the shank. So the code here, the format of the code is the same as all of these other points of interest that we were already outputting. It's just doing it for the centers of mass of those body segments rather than the joints and the endpoints. Okay? So if you're wondering where I got these expressions from, that's where they came from. I had PyDie export them. Now, what those expressions were, if I go back to my code that I uploaded for you guys, is here I had expressions for the horizontal position of the center of mass of each of those body segments. So let's copy those over to my code here. And then my overall center of mass horizontal position of the whole system is the weighted average of those individual segment centers of mass. Okay? So it's going to be mass of segment A times horizontal position of segment A's center of mass, plus same thing for segment B, plus same thing for segment C. Okay? And then that whole thing divided by the mass of the entire system. Okay? So here I have my expression for the horizontal position of the foot and my expression for the horizontal position of the center of mass. Okay? If you look at all of the terms in these expressions, there's some parameters like segment lengths and segment masses and center of mass locations that we already know, so we know values for those things. If you look at the variables in here, The only one that we don't have an already specified initial value for is Q5. Okay, there's other ones in here, but we already know them. We already know Q3, we can freely specify the trunk angle. We already know Q4, we can freely specify the hip angle. And we already know Q1, the horizontal position of the hip. We can arbitrarily specify that. So in this equation up here, where I set horizontal foot position equal to horizontal center of mass position, there's only one unknown in that equation, Q5, and I can solve for that unknown. How you actually do that is where you have a little bit of freedom, and you might do it slightly differently from me. I like to derive symbolic expressions for these things whenever I can that generally, and in many cases, will lead to computationally the fastest way of working with these equations in simulations and in forward dynamics. But there might be other ways that you could do this that will also result in good ways, or in good answers or good values for your initial states. So if I want to derive a symbolic expression for Q5, where I solve this equation up here for Q5, let's first define all of these terms down here in these expressions as symbols. Okay, so I've got LA, LB, LC, RA, RB, RC, MA, MB, MC, M. I'm going to throw G in here because I'm eventually going to need G, and I'm also going to throw KGC in here for my ground contact stiffness. I'm going to need that later too. We don't need it here yet, but I'll just put it in there for now. And then I'm going to need my generalized coordinates, Q1, Q2, Q3, Q4, Q5. Okay, then I will also want my symbols here on the left-hand side, defined as symbols, so P4X, UX, UX, COX, COMX, and I think that's all of them. Okay, and let's just run this and save it. And I'll just call this tester. And see if it's working well so far. Seems to be fine so far. Okay, and so how do I now derive an expression for Q5? You can use the solve command in MATLAB to say, tell me the solution to this expression here, and give it to me as a function of Q5, or solve for Q5. Okay. So here I did P4x minus COMX. The unspoken part of this argument here, this first argument that you give to solve, is that you're solving this equation with it equal to 0. Okay, that the right-hand side of that expression is assumed to be equal to 0. So this is solving the same thing as P4x equaling COMX. And then I'm asking it to solve that equation for the symbol Q5 here. Okay, now let's run that and see what we get. And it spits out here in our command window 2 equations. Okay. Now, it's giving me 2 answers there, because if you dig into these expressions here, Q5 always appears inside cosine terms. And cosine has 2 solutions, 2 arguments that give you an equal result in terms of the value of that cosine. For example, cosine pi and cosine negative pi both have a value of 1. So that's why it's giving me 2 answers here. So we need to figure out which one of these is the answer that we want. So I'm going to copy those, and I'm going to paste them down here. And I'm going to call these my options for Q5. Q5 option 1 and Q5 option 2. Okay, now I want to actually populate the right-hand side of these expressions with numerical values for these arguments inside of them. Okay, I don't want to do this symbolically anymore. I want to actually determine values for Q5 and see which one of these is the right initial angle for my knee joint for setting my initial squatted posture. They're both right in the sense that they both are solved correctly and are both valid solutions to those equations, but only one of them is going to be the one that gives you a realistic human-like knee angle for your initial value for Q5 here. So let's call our model parameters here. We'll do kines79w pars. And then we also are going to need values for our other initial states here. So let's go back to our go function here and copy our initial states and paste them in here. And we don't need Q2, he doesn't appear here. And we don't need Q5, he is what we're trying to solve for here. Okay, and now if I run this, if I didn't make any mistakes, we should get two numerical values here for my two options for Q5. And let's see what we get. Okay. So for my initial Q5, that first expression, when I populate it with actual numbers for my parameters and my variables, gets me an answer of 2.8419, and my second one gets me negative 0.9221. Okay. Remember here, Q5 is the knee extension angle. So if we get a positive answer here, that's a knee extension angle. If we get a negative answer, that's a knee flexion angle. Okay, and in terms of the pose of the knee, it's either, at least in terms of the normal human ranges of motion, it's either in full extension with an angle of 0, or it's in some degree of flexion with some negative angle. We shouldn't see real large positive angles for the knee, at least the way that we have the knee defined here. And remember, these answers are in terms of radians. So if I convert these to degrees, you know, the first one here is an extension angle of 162 degrees. So imagine your knee bending the opposite direction by 160 degrees. Not a very realistic or not a very comfortable result either. Whereas if I convert my other one here, 0.92 radians, 2 degrees, then I get an initial knee flexion angle of 53 degrees, which is pretty realistic, right? That's well within the range of motion of most people's knees. Okay. So it looks like, at least with my approach here, we got two expressions for Q5, two possible options for our initial value for Q5. And this second one, option 2, is the one that we want. This is the one that gives us the correct value for our problem here for the initial knee angle. Now it turns out that at least for sets of initial kinematics here that we can specify that are within the normal range of values that you might set for realistic human angles here, that this second option here, Q5 option 2, is always the one that we want. We never want the answer here from this first option 1. It's always going to produce this weird, unrealistic, very large knee extension angle here, where option 2 is always going to give us the knee flexion angle that we want. So this is kind of nice because now we can ignore this first option, and we can ignore all this other stuff and don't have to redo this every time we might change the initial state here, and can just use this final expression down here, which I'll copy over to my go function as my means of specifying the initial value for Q5. And then let's go to the end here and put a semicolon so we don't print that to the screen all the time. Okay, so I'm partway there. I have my initial knee angle. Okay. Now let's specify the initial hip vertical position. And this one here, we were doing this such that foot is under center of mass. And now with Q5 known, we're going to specify our initial vertical hip position such that the vertical ground reaction force equals body weight. Okay. So to do this, we are going to want our vertical ground reaction force, Fy1, to be equal to mass times gravity. And this vertical ground reaction force, if I go look at it in my model function here, it's a function of P4y, which if we look at, well, what's P4y? P4y is a function of all of our other initial states, which now that we've specified Q5, we know all these, and Q2. Okay. So this vertical ground reaction force here is essentially a function of Q2. And so if we set it equal to body weight, there's only one unknown in this expression. This damping term here goes to 0 because all of our velocities are 0, so no damping. So we end up having just one unknown in this expression if we set Fy1 equal to mass times gravity, and that unknown is Q2. So just like we solved our previous relationship for Q5, we can solve this relationship for Q2 and get our initial value for Q2. So let's go back to our symbolic playground here. And now we are going to specify Fy1 up here as a symbol and P4y as a symbol. Now I'm going to copy my P4y expression over there. And I'm going to copy my vertical ground reaction force expression over there. P4v, the velocity of the contact point, is going to be 0. You could compute it if you wanted. If you want to make this kind of a more general purpose code, for example, you could copy over this expression for P4v, and then you could enter in symbols here for V1 through V5, and then you could get your initial, when you're actually computing things, specify your initial kinematic state with zeros for all those V1 through V5. But since we know for our static squat V1 through V5 are all going to be 0, then this damping term goes to 0. So BGC times 0 here would be 0, and it's just this stiffness term here multiplied by 1. So that term goes away. And then remember, we're going to be calculating the initial height of this contact point through the calculation of Q2, such that this initial vertical force equals the weight of the model, mass times gravity. Okay, so that's why I stuck gravity and kgc up here in my symbols, even though we didn't need them for that first part of the problem. Okay. So let's now solve that expression there. I'm going to say mg minus kgc times P4y raised to the 2. And I want to solve that expression for Q2. And let's run that and see what we get here in our workspace, our command window. Okay. Oh, let's do all this above here before we call our parameters. We want those still as symbols up here. We don't want to populate them with numbers yet. There we go. Okay, now here again, I have two expressions for possible values of Q2, of that initial height of the hip. Both of these will give me an initial ground reaction force equal to body weight, at least the code thinks it will, and then it turns out actually only one of them will. So let's copy these expressions over here. And these are my options for my initial Q2. Okay. And we need a value for Q5 here for this to work. And we're going to use that second value over there, -9221. And then if I run that, I should get two values for Q2. Okay, so two potential values here for Q2, and both pretty similar. So not like my options for Q5 here where they are very different, and one is obviously very wrong and one's very feasible. These are both pretty reasonable heights, 0.8 meters above the ground and 0.79 meters above the ground. Not a big difference there, so which one is right? Generally, it's going to be the smaller one that's correct, because that's going to be the one that has the contact point actually pressed into the ground and producing a ground reaction force. This other one here that's close, that one's going to have the contact point actually slightly above the ground. And why does it think this is a height that's going to produce a ground reaction force equal to body weight if it's not even pressed into the ground? Well, notice here, when I was copying over my expression for the ground reaction force, I skipped this if term, right? I just used this part here, and I skipped this part here where I say, hey, if P4Y is positive, that means we're above ground and the ground reaction force is 0. Okay. So I skipped that. So what it's pulling out here is the negative and positive values for P4Y. So this bottom one here has P4Y slightly beneath the ground, and this top one here has P4Y slightly above the ground by that same amount that the other one was beneath the ground. Let's take a look at what that actually looks like if you're not completely following what I'm talking about there. Let's actually calculate P4Y here. So the P4Y associated with option 1 would be this one, and the P4Y associated with option 2 would be this one. And so option 2 here should, I think, be slightly beneath the ground such that it would produce a ground reaction force in the positive direction equal to body weight. And option 1 here should have the same value as this second one, but should be positive instead of negative. And let's see if that's what we get. Okay, and that is indeed what we got here. So this second one is pressed into the ground by a little bit under a centimeter, producing a ground reaction force equal to body weight. And this first one is that same distance, but above the ground. Now, again, why is it getting this one as a possible value here when it's above the ground and not even producing any ground reaction force? Again, it's because I skipped this if statement in bringing this expression over here so that it's easy to solve algebraically. Solving it algebraically with the solve command with if statements inside here is not easy to do. And in fact, I don't even think it would work at all, at least in this particular case. So it doesn't know that it should be 0 when it's above the ground. It thinks that squaring P4Y here and ignoring the sign on it can give me the same ground reaction force here, when in fact it can't in my actual model. Okay, so I have my expression here that I want for Q2. It's this second option here. And this is also another nice case where, at least for all of the values of initial Q3 and Q4 and Q5 that we will be considering, it's always going to be this second one, Q2, that gives us, Q2 option 2, that gives us the actual Q2 that we want, that has the contact point initially pressed a little bit into the ground to produce body weight in the vertical direction as the initial ground reaction force. So I can copy that one over to my to my Go code here, and paste it in there, and that's going to be where I get my initial Q2 from. Okay, let's do a test here and see if our model is starting in a squatted pose on the ground with an initial ground reaction force equal to the body weight of the model. First, down here, I need to calculate my ground reaction force after my simulation has run so that I can see what it actually is when it was finished. So let's calculate the ground reaction force. So for I equals 1 length t for all time steps. And I've already got P4Y there, so if P4Y is greater than 0, then my ground reaction force is 0. Otherwise, I want to calculate a ground reaction force. It's going to be kgc times P4Y raised to the 2 is 1 minus bgc times P4V. Okay. And I need my expression here for the velocity of that contact point, so let's go grab that and pull it over here. And need some scalar multipliers here. Okay, and if I made no mistakes, that should give me my vertical ground reaction force. And we're going to eventually want to look at the horizontal ground reaction force too, so let's just throw that in there too. And what was that function exactly? What was P4? And then I need my horizontal velocity as well. Oops, wrong one. That is vertical. I want horizontal. Okay, and let's run this for just a short time here and see what we get. Okay, our model looks like it's standing on the ground and looks like it might have a initial ground reaction force of perhaps equal to body weight. At least it looks reasonably plausible. Let's take a look at what we actually got here. For my initial ground reaction force, I got 716.13 newtons, and is that equal to the weight of the model, mass times gravity? And it is indeed. It's exactly equal to the weight of the model. Okay. So it looks like we've achieved our goal here of setting the foot underneath the center of mass and setting the initial height of the hip such that our initial ground reaction force is equal to the body weight of the model. Okay. Now we have one step still remaining here, and let's see what that step is. If I simulate this for an appreciable amount of time, we'll see that our model is not holding a static squat. It is sinking into the ground. That is because we need to specify or revise how we are specifying the initial states of our muscles, the initial activations and the initial CC lengths. Here we have the ground reaction force running straight through the center of mass of the model, so that the ground reaction force is not producing any moments about the center of mass of the model. However, that ground reaction force is producing moments about the joints of the model. It doesn't run straight through the center of the joints of all the models. And also the other external force, the weight on the center of mass of the body segments, are producing moments about the joints as well. So we need to redefine our initial muscle states here so that the initial muscle forces are, 1, static, and 2, are producing moments equal and opposite to the moments due to the external forces, due to the ground reaction force and due to the weight of the model. And when those internal and external moments are in balance, and we have our initial state here specified correctly, which we just did, then the model should finally be standing still in a static squatted pose, and should be able to hold that pose pretty much indefinitely. Okay, this has gotten to be a longer video than I thought, and so we will stop here with the initial kinematic state specified, and then in the next video we will revisit how we are specifying the initial muscle states.